Welcome to this explainer. Have you ever looked up at the night sky and wondered what forces are truly pulling the strings of our universe? Today, we're diving straight into the greatest enigma in all of physics. We're talking about an invisible phantom force that might be tearing our reality apart. Or, if we look at some incredibly anticipated brand new data, it might actually be losing its grip. We're going to explore the absolute cutting edge of cosmology to try and understand exactly what the future holds for the cosmos. So let's jump right in. What exactly is this invisible cosmic engine that's driving the accelerating expansion of space? To really grasp how weird this is, we have to rewind a few decades. For a long time, astronomers logically assumed that the gravitational pull of all the matter in the universe would eventually slow down the expansion after the Big Bang. Think of it like taking your foot off the gas pedal and just letting the friction of the road slow your car down. Makes sense, right? But then, in the late 1990s, observations of distant exploding stars, supernova, revealed something genuinely mind-bending. The expansion wasn't slowing down at all. It was speeding up. Someone, or something, was aggressively stepping on the cosmic gas pedal, pushing everything further and further apart.
It's honestly a pretty humbling reality when you think about it. Everything we can physically interact with, from the blazing stars in the night sky to the planets, right down to the tiny atoms vibrating inside your own body right now, makes up just 5% of the universe. Another 27% is locked up in dark matter, which we can't see, but we know is there because of its gravitational pull. But then there's the rest of it. A staggering 68% of the entire universe is completely dominated by this unseen presence, this mysterious driving force behind the cosmic acceleration.
We call this mysterious force dark energy, and it essentially acts like a repulsive anti-gravity force. And it's incredibly strange. It has a staggeringly low density, about 7 times 10 to the negative 30 grams per cubic centimeter. To put that completely alien number into perspective, that's the equivalent of taking a cubic meter of empty space and finding literally just a few loose protons floating inside it. So how on earth can something so unimaginably sparse completely dominate the fate of the universe? Well, it's because there is simply so much empty space out there. Because it uniformly fills the unfathomable voids of the intergalactic vacuum, it totally dominates the energy inventory of the cosmos. As the universe expands and more empty space is created, more of this vacuum energy appears, completely overwhelming gravity on a macroscopic scale.
University of Chicago astrophysicist Michael Turner actually coined the term dark energy back in 1998, and his quote perfectly sets the stakes for our cosmic detective story. Until they definitively figure out what this force is, we simply cannot sensibly guess the ultimate destiny of our universe. Now, decades ago, Albert Einstein famously proposed a cosmological constant, which was basically a mathematical fudge factor he added to his equations to keep the universe static. He later called it his biggest blunder. But the discovery of dark energy suggested his blunder might actually be real. So is it an unchanging cosmological constant, or is it something else entirely?
Part 1. Tension in the cosmos.
Now, we've got a massive mathematical problem on our hands that's literally fracturing everything we thought we knew about physics. It's a stark contrast known as the Hubble tension. Basically, we have 2 different ways of measuring the expansion rate of the universe, known as the Hubble constant. On one hand, we can look at the early universe using the cosmic microwave background. That's the oldest light and the literal afterglow of the Big Bang. When we measure that, we get a predicted expansion rate of about 67.4 kilometers per second per megaparsec. But on the other hand, when we measure the local universe directly, using the pulsing light of nearby stars and supernovae, the rate comes out much faster, at about 73.0. Why would 2 perfectly sound mathematical methods give us totally different speeds?
Listen, in the realm of high-precision cosmology, a discrepancy of this size is an absolute disaster. It's reached what physicists call a 5 sigma level of statistical certainty. This is super important to understand. A 5 sigma event means there's roughly a 1 in 3.5 million chance that this difference is just a statistical fluke or a measurement error. 5 sigma is the literal gold standard for declaring a true discovery in physics. Because the numbers are so undeniably conflicting, it forces us to ask a pretty terrifying question. Is our standard model of physics broken? Are we completely missing a phantom menace of new physics? Maybe an early burst of dark energy shortly after the Big Bang that altered the trajectory of the cosmos?
Part 2. Is dark energy evolving?
And that brings us to a groundbreaking new investigation from the Dark Energy Spectroscopic Instrument, or DESI for short. These folks might have just blown the case wide open. Located atop Kitt Peak in Arizona, DESI mapped the cosmos with unprecedented precision. Using 5,000 individually targeted robotic eyes, they captured the light of 15 million galaxies. The secret to their method is something called baryon acoustic oscillations. See, in the very early universe, everything was a hot, dense soup of plasma, and sound waves literally rippled through it. When the universe finally cooled, those sound wave ripples effectively froze in place, leaving behind massive spherical rings of dense matter where galaxies eventually formed. By finding these rings, physicists get a fixed, unchangeable cosmic ruler. They use these ancient sound waves to meticulously track dark energy's influence across 11 billion years of history, looking for any subtle fluctuations.
And the results from mapping those acoustic oscillations? They are sending massive shock waves through the physics community. They found a tantalizing 4.2 sigma confidence that dark energy is not a constant. This means the idea of an unchanging property of the vacuum, Einstein's famous cosmological constant, might actually be completely wrong. Instead, the data suggests dark energy is actively evolving. While it might have intensified in the distant past, the DESI data hints that our universe's ultimate engine actually started losing steam about 6 billion years ago.
As one of the DESI spokespersons pointed out, the simplest explanation for what we see in the cosmos is suddenly shifting right beneath our feet. If this great engine of the cosmos is indeed sputtering out over time, it radically rewrites our long-term predictions. If dark energy doesn't act like a constant and is instead a dynamic, changing field that can weaken, what happens to us? What happens to time, space, and the ultimate end of all things?
Part 3. How will it all end?
Depending on exactly what dark energy decides to do next, the laws of physics essentially give us three distinct doomsday scenarios. If dark energy acts as a true cosmological constant, just unchanging forever, we get the big freeze. That's a cold, lonely heat death where galaxies drift so far apart the night sky goes black and stars burn out one by one. Now, if dark energy acts as phantom energy and increases in density over time, we get a violently explosive big rip. But if the new DSI data is right, and dark energy is a dynamic field that's currently weakening, we could face a terrifying cosmic reversal known as the Big Crunch.
To really understand the stakes of these fluctuating fields, let's look at the absolute worst-case scenario first, the Big Rip. If dark energy were to strengthen over time, we'd see an incredibly violent end to reality, accelerating at an unimaginable pace. Roughly 200 million years before the end, the sheer expansion of space would overcome the gravity holding galaxy clusters together. By 60 million years, the Milky Way itself dissolves. Fast forward to 3 months left, and the gravitational bonds of our solar system fail. The Earth gets ripped right away from the Sun. At 30 minutes, the literal planets explode as the expanding vacuum overcomes molecular bonds. And in that final, microscopic fraction of a second, your very atoms would be sequentially ripped apart. Space-time itself just shreds into nothingness.
But hey, good news. Because the new DESI data strongly suggests dark energy is actually losing steam rather than gaining it, we might be spared from the cosmic shredder. The Big Rip is highly unlikely now, but that leaves the door wide open for a completely different yet equally dramatic fate. If this dark energy field continues to weaken, or even drops into the negative, gravity could eventually become the dominant force in the universe once again. Imagine watching the expansion of space come to a dead halt. Then, incredibly slowly at first, galaxies would begin rushing backward, moving toward each other. The cosmic temperature would skyrocket, the night sky would become blindingly bright, and eventually the entire universe would close in on itself, crushing all matter, light, and space-time back into a single, unimaginably hot singularity, the Big Crunch.
Part 4. The ultimate cosmic mystery.
So, as we wrap up this explainer, what are the big takeaways? Well, we've learned that dark energy is definitely not just a fringe theory. It completely dominates reality, making up 68% of the universe as a pervasive anti-gravity force. We've also seen that the 5 sigma Hubble tension is a massive red flag in modern science. It practically demands a fundamental rewrite of our standard physics. And perhaps most critically, the latest precision data from DESI implies this invisible engine is finally slowing down. This is monumentally important. It challenges nearly a century of assumptions about a constant expansion and fundamentally reshapes our mathematical models for the ultimate fate of reality.
Which brings us right back to you. Based on the monumental evidence we've explored today, whether it's the slow, freezing cold, the violently accelerating rip, or the fiery, crushing collapse, which of these cosmic fates do you personally think is most likely? Drop your favorite doomsday theory in the comments below. Thanks so much for learning with us, and don't forget to hit like and subscribe so we can keep unraveling these incredible cosmic mysteries together in our next explainer. Catch you then.